Recording. Okay, so we are recording now as a follow-up to because the stream failed. Sorry about that, but if you're seeing this, then it's already been posted. All right. So to remind us of what we're doing here, we're doing a pre-order traversal, and the way that that is usually presented as is you do the route, then you go to the left if it exists, and then you go to the right if it exists. And then once you're done with that, then you go back up, and there's kind of like a recursive idea here, and that's how it's usually presented. But I'm going to show you the stack-based version of this because, of course, stacks are better than recursion, right? So what we're going to do is we're going to start at the root, A. Right? Oops, I want my highlighter here. A. We're going to process it. Then we're going to go to the left, and then we're going to go to the right. So by process it, I simply mean that I'm going to print it out down here. Process order. Right. Now I want to go to the left, and I want to go to the right. But before I do, how am I going to use my stack to remember where I still need to go? What if I pushed its children? What if I pushed the left child first and then the right child? B, C, right? Remember, this is a stack. It's growing upward. This is the bottom of the stack, and this is the top of the stack, okay? You push things onto it, on the top, and then you pop things off of it. Except that if I went in the order of left then right, with the stack being a last in, first out data structure, what's going to happen? Where do I go next, according to the stack? Sorry. If I'm looking at the top of the stack here. Let me back up here a little bit. How does this entire process started? I start by pushing the root itself. And then I pop it off the stack and process it. Right? At this point, I am done with processing A. I now need to go to its left child and then eventually to its right child after I've done with the entire left subtree down here. If I push it in that order, though, B, C, and then I look at the top of the stack, where does it tell me to go next? To the right. It's in reversed order, which makes sense because a stack is a last in, first out order. So what order should I be pushing them in? Push right. Push right, then push left. Okay? So I'll push C, and then I'll push B. Okay? Next iteration, what do? I pop it off, pop whatever is off the top here, B, and right now I am at this location. Right? So I process it, and it ends up getting added down here in the process order. And then I push the right and then the left. But I'm at B right now, so right and left mean E and D. E, D. Right? I continue this process. I pop whatever's on the top, and this is my current. Right? So I've popped off D here, and now I am at this location. Right? I process it. Right? I process, then push right, and then push left. So by processing, I'm going to process D, right? And then I push H and then G. Right? And you see my stack growing here, and it's keeping track of the things that I don't forget about the right subtree, right? I need to eventually return there and take care of that. Okay. So let's speed up the process a little bit here. What comes off the top next? G, and I push M and L, and I process G, push M, push L, and at this point I am done with G. What gets popped off the top next? Oops. L, and so I process L, and I push what? Does it have any children? Nope. So I end up not pushing anything. And that's done. And you can see the pattern here with the highlight. Right? I'm going all the way to the left. After once I've hit a dead end in the maze, then I start backtracking and going to the other directions. The way that I've done that is by keeping track of all this stuff over here. So what's the next thing that gets popped out the top? M. Oops. I push its right child and then its left child, but there is no right child to push. So I push R. Right? I process M. Right? And again, now let's go ahead and speed up the process a little bit. What's next? R. And when I've gotten to that point, I have processed this entire tree, subtree so far. Oops, it looks like I never erased G, did I? Sorry about that. G was no longer in my stack, right? Because I would have deleted it when I processed it right here. Just a mistake, sorry. Next one is going to be H. Oops. I process H, and then I push right, I push left, but there is nothing to push there, so I end up not pushing anything. Right. At that point, H is processed, and then N gets processed next, and it's off the stack. And you can see here that remember that I needed to remember that C, I still need to do that. I still need to do E, and they're still in the stack. So I not magically, but now I pop those off the stack, and I'm back to where back to this point here, where I went to the left subtree. I went down that corridor. Now I need to go down this corridor. Right. So, what's the remainder of my process times here? E, then I, then O. At that point, I am done. Oops, I'm done with this entire left subtree. And I continue with C. What's the rest of it? C, F, J, P, Q, and K. In fact, if you only have a 3-node tree, A, B, and C, what is a preorder of this? A, B, oops, B, C. There are other ways of doing this. You don't have to go root, left, and right. An alternative would be to wait to process the root until later. Right? You could go with left, then the root, then the right. Or in this case, it'd be B, A, C. Right? This is called an in-order traversal. And we'll discuss that next time. You could do it another way. You could go with instead of delaying it the root till between the two, you could delay the root until after you've done both the left subtree and the right subtree. You could go left, right, and root. Or in this case, it would be B, C, A. And this is called a post-order traversal. And you can see where we get these names. Preorder, in-order, and post-order, it's where the root is. Do you do it before everything else, in the middle of everything else, or after everything else? All right? That's preorder, in-order, and post-order traversal. You might also be asking yourself right now, well, there are a couple of other orderings here. If I've got A, B, C, I could list all these permutations out, right? I've got BAC, I've got BCA. What's another permutation of these three? CBA, right? ACB, right? And what's the other one? CAB, right? Well, let's just take this one, for example. A, then C, then B. That's the exact same thing, just a mirror image, right? It's just preorder traversal reversed. One of these is going to be post-order traversal, but reversed. The other one is going to be an in-order traversal, but just reversed. So who cares? Left children become right children, right children become left children. We don't generally consider these three over here. Why? Because we read things left to right, top to bottom in English. Okay? We only consider these three orderings right here. with the remainder of our time today, what I want to do is I want to codify this. First of all, let's write some pseudocode. And then what we're going to do is we're going to program it. Okay? So here's my pre-order traversal. All right? My input will be a tree T. Right? Represented how? By its root. Okay? And my output will be a pre-order traversal. Okay? Now, let's codify what I did over here. Okay? Well, what did I do first? I established what? This stack. Right? How did I get the ball rolling? I took this root and I pushed it into the stack so I'd have a starting point. So that much we can do at least. Right? S will be a stack. Okay? And what I'll do is I will push T's root onto S. Okay? Now let's go back and ask ourselves, what did we do? We popped it, right? Then we processed it, then we pushed the right child, if it existed, and then finally we pushed the left child, if it existed. Right? We went through this process over and over and over again, until what? Stack's empty. Right? So, when do I keep going? While the stack is not empty, I'll do those four things, right? U will end up being s.pop, process U, and then finally push U's right child, push U's, U push U dot left child. Here I'm using kind of a C style syntax in order to, the dot operator there. Of course, if it were, if it's Java, which we're going to be doing here in a second, I would actually get the left child, get the right child. And that's it. Right? Once I break out of this loop, I've processed everything. Okay? Let's get some practice, Java-wise, and do it over here. By the way, was our pre-order traversal correct? A, B, D, G, L, M, R, H, N, E, I, O, C, F. Yep, looks good to me. And not only that, but we have now a built-in, at least ad hoc test case that we can use to see if we're actually correct here. Okay? In-order traversals, post-order traversals, etc. And we'll get to the rest of them later. So I'm going to actually implement this as the toString method, but I'm going to do it as a different method. Public list of elements, pre-order traversal. Right. Now, why am I returning a list? I want to return this thing right here. Right? I'm going to do this in a pre-order traversal, and processing it simply means that I'm going to add it to the end of the list. And then here you go. Here's a list containing all the elements in the tree, but as a list. It's been dumped in a pre-order fashion. Okay? So, my pseudocode here. What's the first thing I do? I establish a stack. Right? In Java, there is a stack, but it's much easier to use a deck. Remember, a deck can be a stack. It can also be a queue. It's a double-ended queue. What's it going to hold here? Nodes, good. It's going to hold a tree node, also parameterized on T. Right? And I will call it a stack, right? Is equal to a new deck. There. It's not going to let me do this. Why? Cannot instantiate the type deck. Do you remember? Did you read RTM about decks? If not, you'll want. Well, I think that we're telling you to use a one in particular implementation of a deck this week, that this is just an interface, right? What could we use as a deck? Well, we could use a stack, but a stack I think is just another interface. What's an implementation of a stack that hopefully you'll be doing tomorrow? A linked list, right? We'll also need a result here. So list of elements here, not tree nodes, because I'm going to be taking things out of those nodes and putting them in. A, B, C, D, E, F, G, O, right? These are characters down here. You'll see here that I have a binary tree that holds a bunch of strings. Right? So this is my result. I'll just make it into an array list. And that's ultimately what I'm going to return. Okay. Now, how do I get the ball rolling? I've got a stack. I've got my result. I push the root onto S. Okay. Stack dot push this dot root. Now you got to be careful here. What's one edge case? The root's null. In other words, it's an empty tree. If the root is null, then I probably just want to stop immediately and return. Right. Here you go. Here's an empty list because the tree is empty. Otherwise, I'll push this, the root onto the stack. Right. Now I need to go into my while loop here. Right. While the stack is not empty. Is empty. But while it's not empty, then I process or pop the top of the stack. 2, I process the result, the popped element. 3, I push the right child if it exists. And 4, I push the left child if it exists. So, how do I pop it? Tree node. I need to save that off as a result. I'll even use the same variable name here, u. Why? Because, well, what is it? It's just a node, right? I can't call it, I shouldn't call it, I could call it n if you really wanted to, but what have we been using n up to this point? The size of an input, the number of elements in the node or something like that, right? So I could use x and y, but those are kind of used for graphs, right? X-axis, y-axis. So what's left over? U, S, T. So I'll just go ahead and use U here. Right? Is equal to the stack dot pop. I will process the node, and again, for processing, that simply means in this case that I'm going to add it to the result. Do I add the tree node though? T dot get value. Okay. Now I push the right child if it exists, right? If I don't make a check for whether or not it exists, what will I end up pushing? Null. And I don't want to do that, right? Or I could write code such that if I pop it off the stack and it's null, okay, keep going and throw it away, right? I'm not even going to do that in the first place though. If u dot has right child, right? Note those nice little convenient methods allow me to write things in a more Englishy way. Right? U dot has, if it has a right child, then push it. So stack dot push u dot get right child. And likewise, push the left child if it exists. U dot has left child. I will stack dot push u dot get left child. And that's it. Except that, what are you complaining about? Too many parentheses. I didn't put that there, you did. Autocomplete. All right, let's try it. Well, if I ran it right now, I would get to do, right? Because the toString method is simply just calling to do. So what I'm going to do is I'm going to change it so that the toString method instead calls this other method and then calls the toString method on the resulting list. All right. Now, if I run this, I should expect, again, this is the same tree as before. I would expect that we did graphically over here, right? And that's gone now. But anyway, I should expect this right here. Right? Crossing my fingers. ABD, GL, M, R, H, blah, 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 P, Q, K. Looks good to me. And with 15 minutes to spare. Let's take that 15 minutes and think of another way of doing this. I presented a stack-based solution immediately because recursion is bad in general. What would a recursive solution look like here? Let's write it just to find out what it looks like. Public list T, recursive preorder traversal. Right? So what I'm going to do is I'm going to establish, do I need a stack anymore? Nope, because I'm going to abuse the call stack to do this. That's what recursion does. It simply abuses the call stack instead of using an in-memory stack. So I'll have a result here, and then I'll return result. Right. Now think about this recursively. And for this, I'm going to restore this over here. All right, and come on, reconnect. There we go. All right, remember, I'm at my current node. I need to go to the left, and then go to the right. But in this case, I'm going to abuse recursion and the call stack to do all the work for me, so I don't have to keep track of any breadcrumbs. The call stack, the program stack, and my stack frames are keeping track of my breadcrumbs for me. So what I'll do is I will process the current node, and then what? Recursively call left, and then recursively call right. So in other words, I am going to have an input here of the current node. To do that, I'm going to define another function here, private recursive preorder traversal. And I'm going to have to be given a private void. Right? I'm going to have to be given everything as input to this recursive solution that I need. I need the current node, which is a tree node, T, current. Okay? Once I have that, I need to, 1, process the current. 2, recursively call this method on the current's left. 3, recursively call this method on current's right. Okay? Recursively. All right, there we go. So what does processing the current mean? Same thing as before. Put it in a list. So list.add current. That means that I need to be passing the list on along with the current node so that you can deal with it, so that this method can deal with it. Right? So a list of elements, the list. Okay? And what are you complaining about? Oh, current dot get value. Pull the value out of the node. Right? Then recursively call this method on current's left, if it exists. Right? You don't want to be doing the recursion if there's nothing there. Right? If current dot has left child, then recursively preorder traversal, we will go to the left child, so current dot get left child, oops, and pass through the list. Likewise, if current dot has right child, then same thing as before, but current dot get right child and the list. What's the very first thing that you, oh, I should have put that below the 3. What's the very first thing you do when you think recursively? Base case, right? You need to stop the recursion at some point. We folded that in here. What's the base case in a recursive solution? It's when you get down to a leaf and there's nothing there, right? But we don't even get to that point because we don't make that recursive call if there is no left child. We don't make that recursive call if there's no right child. So we've taken the base condition and we've folded it into our control flow down here. Okay. Now all I need to do is call this function from up here on this dot root. That's where you start, and the result list. Cool. One other corner case here is, again, we need to take care of the possibility that it's an empty tree, in which case we simply just return without any recursion whatsoever. Okay. Let's try this one. Instead of doing a preorder traversal, let's do a preorder recursive traversal. We should get the exact same thing, and we do. Right. So, take a look at this. Sans comments here. Right? 1, 2, 3 lines of code, essentially, if you roll in the base conditions there. Right? That is one of the few instances in which I would say, yeah, recursion seems pretty okay there. Right? Except that if you had a really, really large tree, if you have a really, really large tree, 1 million elements, guess what? Or depth of 1 million. What's going to happen? Function calls function calls function calls function 1 million times, and we have a Stack Overflow. My solution here with an in-memory stack, 1 million items, that's 4 megabytes of data. It's going to run just fine. Right?
How big are your home stacks?
That's a good question. Java stacks, I'm not sure, but on the order of megabytes or kilobytes if you're in an embedded system. And so you do not want to abuse the stack in those cases. I think on the default stack size on CSE for C programs, or for programs in general, I guess, is 8 megabytes. So on the order of a few 100,000, because a stack frame is going to be all the local variables, return register, a bunch of other things. So even say like just 40 bytes, right? That takes it down to only a few 100,000 function calls in your recursion. Right. All right, any questions? Otherwise, I will stop the recording. Sorry it didn't work today, but I will go ahead and upload it as soon as I can. That statement is irrelevant because if you're hearing it, then it's already up.